Hey, welcome everyone. Today we are happy to have Koushik Ray from IACS. He's going to tell us about Bootstrap equation from conformal integrals and the GG system.
Okay. So good morning, and let me start by thanking Puneet for this very kind invitation. It's interesting. I'm giving a talk here in this room after 30 years actually. Last time was in 95. So that time I had a few years into my PhD, and now I'm within a few years of my retirement. So this kind of closes the bracket, I guess. Yeah. So the thing that I wanted to discuss with you is this thing announced based on this post papers. This paper should be on the archive today. I think today. So here the plan. So I'll start with some very vague, non-rigorous statements, which almost everyone knows, I guess, about this, the thing that we want to do about conformal bootstrap program. Then I'll talk about configuration space of points and representation of the conformal group. Then I talk about conformal correlation functions as representation of the of the conformal group in the configuration space of points. Then connect it to things called conformal integrals and write conformal integrals. I'll introduce these jargons, different systems, and then rewrite conformal integrals as a GG system. I'll explain what GG system is and write down the bootstrap equation and conclude. This is going to be a toy model. Everything we're talking about is called CFTs in any dimension, but only with scalars, without spins. It's kind of a toy model. I just try to impress on you that this connection with GG system has some hope of, in the bootstrap program. That's basically what I'm trying to do. And if you are worried about all cons here, I guess pros are all here. So I'm going to talk about only cons. Yeah, so let's start with this. These are our desideratum. Let's start from the scratch. So phi is a scalar field on a manifold. This manifold is always RT Euclidean flat space for me for the purpose of this talk. And it has a scaling dimension or conformal weight if it transforms like this. So if I scale the space-time coordinate with a lambda, it goes as lambda to the power delta, and this delta is called conformal weight. Lambda being a non-zero real number, and fields are taken to have a multiplication rule like this. So two fields with two different weights at two different points that are taken to satisfy a multiplication rule like this, that expanded in some kind of a basis of themselves, where these things are constant, real constants, C with three indices, three conformal weights. These are called OP constants. There is a space-time dependent part here with a certain index, and then other fields in the theory. That's more or less the structure of the OP. This is called OP is for operated product expansions. And the question you want to ask is how far. So this is a CFT data, the deltas and the C's.
Shouldn't Xij come with a negative power of delta equals delta?
That depends on how I
define the deltas.
How I write this. I could have written this as delta K minus delta I minus delta.
Sure. Let's
Is there a mistake here?
Yeah, I'm just wondering, doesn't the
probably there's a side mistake there. Yeah, thanks.
No, it's correct, right? Because the singular K appears if
I have to check this thing. Okay, I thought this is correct, but it has a minus sign.
If it is heavy operators, then there should be regular. Delta K large, there should be regular.
Yeah. So there will be minus sign. There will be minus sign.
Like identity.
Right. Yeah, this is minus sign. It will be corrected in the next slide. So this is a typo. Yeah, thanks. Yeah. The question is, thank you very much. That typo. How far can the CFT data be restricted on very general grounds without considering models? So basically it's asks what is the set of values of delta, what is the allowed values of delta that are there in a CFT in general, and can I somehow talk about restrict?
sorry, very sorry.
We are starting.
Okay.
How far can we restrict the OP coefficient, or can we do it at all? So this is more or less the broad goal of this Bootstrap program. So what the idea is,
Are you going to think about unitarity also, or just?
that is part of this. Yeah. So I'm saying that these are more or less the questions that you have here. I will not talk about unitarity. I'll assume it is for this talk.
Really, really sorry. Can you just show your first slide with the bootstrap equation? So
I've not written the Bootstrap equation yet.
Okay.
Yeah. Yeah, I'll write it. Yeah. So the idea is the following. So you define correlation functions of these fields, n number of fields, where deltas are the weights of n number of fields, and this is x1 to xn each in RT. And then the correlation functions transform as this. When you multiply all of these x's with the same lambda, it has this transformation rule. And therefore, this correlation endpoint correlation function furnishes representation of the conformal. I mean, so you extend it, this is just scaling, but then you extend it to say that is a representation of the conformal group. And here's the Bootstrap equation. So the idea is, and I have written it for 4-point functions, but it's typically you would like to do it in general, that you take some endpoint correlation function, and so you have 4 fields like 1, 2, 3, 4 in the and then you permute these fields, these indices around, and assume or demand that they give you the same correlation functions. That's the Bootstrap program. And then using that, you try to somehow constrain the C's and the deltas as much as you can. That's more or less the philosophy. So, yeah. So that's, yeah.
So then do we expect this just one constraint to fix everything about the CFT, or do we also?
You don't want to fix everything about the CFT. You want to fix to a class of CFT. Yeah.
But like,
as far as you can do.
The question is do we need more constraints? Like, for instance, like something like a torus partition function.
That's what I'm saying. So,
Modular.
yeah, of course. If you want to fix everything about the CFT, you need a model. For a particular, given a particular Lagrangian or Hamiltonian or whatever, you can fix stuff. I don't want to do that. The question that one asks is, without going into a particular example, how far can we fix using symmetries and probably a few more ingredients like Bootstrap, like unitarity, as Avijit says. So
I guess
more or less on the general grounds.
I guess the question might be, can you classify all
Right.
unitary CFTs by demanding if you
This much.
conformal bootstrap plus module invariance?
I believe that's true. That's a true statement, right? Like conformal in modular bootstrap, like modular.
No, there you have central charge, etc. to classify, right? So try to classify as much as possible. Then, yeah, so you don't want to fix everything. That's not the idea anyway. So how much symmetry and maybe some of these, some general principles can fix it.
No, but for instance, like let's say I go to the 5-point function.
Yeah, we'll have to, that's as I said, this is an example.
Okay.
So in a 5-point function, you have to impose Bootstrap once again, try to find out, yeah, so it keeps on going.
I mean, so
There's a general idea that after 8 point, you will not have new constraints.
I see. So you have to keep imposing these
Oh, yeah,
constraints
that's
at
a-
8 point.
But that's an assumption, or is it?
That's more or less, yeah. So if you break this into 8 points into 4 points, actually, you see that if you consider 8-point functions, you've actually considered almost all the 4-point functions, and maybe more or less, yeah. I don't think this is a proof, but I think this is a general expectation.
I don't know, I mean, why points is necessary. So, I mean, just the general counting, I mean, if you just do a counting, like so many equations are there. The equations are, roughly speaking, it's of course infinite dimensional, but it's
That's the problem, infinity.
finite times to the power 4, right? You have these weights that you have.
All of them, yeah, I see. All of them will not, for example, if I just change delta 1 and 2, this is not it's not going to change anything here. You need to somehow consider in equivalent permutations.
Yeah, but order, just as an order, it
Yeah.
would be number of operators to the power 4.
Yeah.
Those many equations are there. And the data that you want to constrain is the C delta 1, delta 2, delta 3. So number of operators, 2. Right? So roughly speaking, this should be sufficient. But of course, as in 2 dimensions, we know that there is modular symmetry, that modular invariance that will be necessary. In this case, I'm not sure whether if you just look at the entire system.
Actually, to me, with some very preliminary calculation, it looks like even this is enough. high point will actually.
No, but something even more striking is true, right? For example, the thing that people show with this icing model, 3D icing model,
Yeah.
they consider two correlates.
Two correlates.
Just two
That's
correlators. And they're able to narrow down the icing model.
Icing model, that's right.
Right. So
Yeah.
what is the, I don't think people understand why just considering two
Yeah.
correlators, you are able to precisely pick out the conformal dimensions of first and second primary.
Yeah, so I know, so that as I said, so there's a general expectation that up to 8 will be enough. I don't think, I personally think that much less will be enough. But yeah, and there's no general proof of this technique.
And sorry, you must go on, but all this assumes that the theory is unitary, right?
I'm assuming unitary.
And if you don't have it, I mean, to some extent, suppose, for example, you have the OP but not unitary. Would you get anything like this, or you have to throw everything out?
No, for example, in 2-dimension, we have beta systems which are conformal and non-unitary.
Yeah.
So in principle, one can have those.
So you can have those, but can you constrain them? In the absence of.
So if I, so near the end of that, so as I said, so I'll not, so I mean, whatever I do, I assume, I impose unitarity by hand. So you'll see in the end that even if I didn't assume that, it seems things will go through. I have not checked how much.
So just, sorry, one moment. So I exactly looked at this question once. In the absence of unitarity, what can we say? So first of all, the fact that you were able to just look at one single equation, right, with the lowest primaries, that is not going to
That's not going to.
that's bounded, even with two equations. But if there is a way to look at the entire family somehow using a lot of representation theory,
Right.
perhaps there is a consistent set of solutions. So I wrote down some solutions, but not clear. I mean, the unitarity was not there, and the solutions were written down in principal series and so on. So it was not quite clear how it ties to.
Principal series will be unitary. Finite
but-
dimensional walls will not be.
Well, depends on what one means by unitary, right? I mean, it's unitary from a conformal representation theory point of
From
view.
the representation.
Right,
standpoint.
but in
I see.
model, in
Okay,
unitary
okay.
systems,
Yeah, so
origin unitary,
that's another problem.
that's a different unitarity.
Yeah, that's another problem. You see, there are two unitarities that one is talking about here. One is about the unitarity of the theory that I am defining on the space-time. The conformal group is much in a 2 dimensions higher. So whether you want a unitarity in the conformal group representation or in the Lorentz group. So that's another question. And
But you must go on, but later. But if I just wanted unitarity in the conformal group representation, then what's the story? I mean, all of this is of interest, sort of in discipline and all.
Yeah,
So it's even more crazy.
This is
That's
a-
more
yeah,
crazy.
yeah, yeah.
Calculated that the solution said that obtain somehow relevant participants, but I didn't push that.
It has to be. It has to be. The non-unitary solutions and representations of the de Sitter group, essentially. Because these are essentially de Sitter and de Sitter groups, right? The conformal group is just 2 dimensions higher.
Okay, sorry.
Yeah.
Please.
So the point, okay. In the end, after everything that happens is that you cannot actually restrict the deltas.
So it was just one comment that usually, we are flexible with time.
I know,
So-
Anthony told me, and this is fine with me actually. I prefer that.
Yeah.
Yeah.
Just
So
so that,
yeah, this is like a discussion rather than yeah.
So while write this equation, do we need unitarity to write like just this?
As I said, so at this moment, I'm not imposing anything.
Just
This you can write. This is the principle that one is saying. Polyakov told us that okay, this is a good principle, and people believed it. But yeah, so you might want to put in unitarity as something is saying. So
So you have one question. So isn't this not just the fact that fields are commuting?
which one?
Phi x1, phi x2, and we just.
Yeah, here I'm scalar case here. Yeah.
No, not just that. I mean, they're also commuting.
Yeah, commuting
We're not
is
saying there's any time like.
No. These are only RT. Euclidean, so I can't call it.
So they are commuting.
Yeah.
follows
So-
from state operator response.
Right, that's right. Some of these results seem to be going through for Lorentzian signatures as well. I try to pinpoint where I am not sure. Yeah, so should I? Yeah. So now it turns out that I actually cannot do much. So all one will be has to be content. Oneself with some kind of bounds on the deltas, the weights. That's all we can do after a lot of stuff.
What do you mean by that? I mean,
So some kind of-
three-dimension people can, as I said, pinpoint rising model, right?
That's what I'm saying. You can pinpoint
Not
ID.
just the bound, point. You get-
I'm talking about again general stuff. In general,
No, but I'm saying there are examples where people have
Yeah.
pinpointed using this set of equations.
yeah, but I'm talking about in all dimensions and all kinds of things.
What exactly is the statement? Can you say the statement?
I'll come to that. I'm simply saying at the moment that, for example, unitarity is a bound on this. Unitarity gives you a bound. So similarly, just using the bootstrap, I can actually have a kind of a lower bound that the delta have to be bigger than something. That kind of bound. So I cannot just tell you that this is exactly what I need based on just these general principles. Yeah. And so I'll go through these three different things, and I'll try to convince you that this is not for just fancy mathematical stuff. I have some. I actually need them to do what I'm doing. So I like to formulate a conformal group in terms of some Clifford algebras. That's part of a mathematical topic of geometric algebra. I'll introduce a little bit of these notations and tell you how to write this. This is actually, it turns out this is a 100-year-old thing that was known. I learned it recently, but this was done a long time back. Then I have to, I have two slides on this representation of configuration space of endpoints. This is something we have actually done in classical mechanics when we studied when we talk about before rigid body stuff, that n particle system. 10 particles move in a configuration space. We talk about configuration space of endpoints in classical mechanics. So it's basically that with some extra complications. And then I'll express the correlation functions in terms of these decayed systems, which from instead of geometric algebra is not algebraic geometry. So,
So sorry, point to the extra complications when the particles come on top.
again, this is a very old problem and it's not a completely solved problem. So now let's start with the technicalities. So as I said, so I'll start with this. You can call it PQ in general. And I'll start, I'll assume that this is the quadratic form of this kind. So P signature P minus Q. And these are notations. So this is the x dot x is this, and so it's called mod x square. And conformal transformations are angle preserving transformations from this M to itself. That's the definition of a conformal transformation. This is what one does. One takes X in this manifold, embeds it in a bigger manifold, 2 dimensions high, which has coordinates the same X and with 2 coordinates added to it, U and V. Consider a cone here. This is the quadratic cone. So X dot X is UV equal to UV, so that's here. So you have this map that maps this to this conformal cone. It's called also conformal compactification because this is a close, all sequences here are converse. So this is a way to construct a conformal compactification because I need a conformal compactification because we'll talk about integrals, and unless I have that, all my integrals will diverge. So one cannot simply use RD here. One has to use the conformal compactification, which is defined in this way. So and once I embed it in this 2 high dimensional space, which I write as M circ, this space, this angle preserving transformations here are orthogonal transformations here. So I add this with an orthogonal transformation T here, then bring it back by this projection. So first I embed M into this cone with this I, do a orthogonal transformation here, and then come back with the pi. Pi is setting your X by so this is a map. So I take X by phi, so that takes away the scale, and this is the set of conformal or angle preserving transformations here.
So both that is to be identified, right? Meaning
Right.
a homogeneous x, so xu going to xu, v going to lambda times xuv.
So
that is being identified.
that's equal, yeah, that's it. So that's why it's a compactification. So that's why I said all the any sequence will converge there. Yeah.
And then this lambda, you're identifying for lambda only positive or for all lambda?
And yeah, this is Z2 here, so all I'm positive here.
So what is the role of the Z2?
That's changing signs, as you said. So this is homeomorphic to SP cross Q and then there's a Z2. Yeah. So that means I'm modding out with Z2, so it's only.
So if you did that with the ray, then you would get SP times SQ. But if you did with both the entire real line, you would get this extra Z2 piece, which you perfect.
So there's a.
Are we saying something more than the null cone construction?
This is the null cone construction.
And which is the null cone in M? The C is the null cone.
This is not a null cone in M. This is a null cone in the M set in 2 higher dimensions. You embed this in a null cone in 2 higher dimensions for the compactification. Compare this with the compactification of C2 with the stereographic projection. That's precisely what you do. The projective compactification of C2 when you write it, C when you write it as a sphere. They bring in the point at infinity.
In this notation, what is the null cone?
This one.
C is the compactified null.
Compactified null cone. Compactified because you have this scaling there, which it mentions. And this is x dot x is uv in this. So x here uv or extra.
So it's a little x on which conformal transformations act non-linearly.
Yeah.
And you also have a capital X
I have a capital.
on which it acts.
That's the capital. That's the capital X.
This P for M circle.
So this is a projectivization. This is the taking out the lambda, as Vijay mentions. Yeah.
I just wanted to make sure, I wanted to ask you about exactly that example of C. So there I would start with 2 coordinates, x1, x2.
Yeah.
And then you would add uv, if I'm right.
Yeah. You can do that.
And that, I mean, I
There
don't
we
normally
actually,
think of,
that's it. There we are not talking about the conformal. One is talking about only about the conformal, so-called projective compactification. So you extend it by a lambda, right?
Yes.
So you can think of this as Z lambda and then with an identification. So that's the projective compactification there. It turns out in 2 dimensions, this will all give the same result.
But just to make sure, so normally I don't think of the point at infinity in quite such an, after identifying in quite such an abstract way, but just to understand it, so you'll have 2 coordinates x1 and x2.
So you have this basically.
And then you identify x with lambda x, u with lambda u or something. What do you do? Yeah, please go ahead. Sorry.
Yes.
Just
So
help me.
you do a projective.
So you identify all points along the race.
So it's that's right. So this is basically, so starting with this, you write down the set of this rays there.
Rays, yeah.
So that's basically the same thing. If you scale each of it, if you scale them, they remain the same because on the right side you have 0. And then while coming back, you are dividing by phi. So that takes away. So that tells you that this is like a projective thing.
This is this standard consumption. So if you look at the conformal group in R dimension.
No, what Sandeep is asking is about this thing, the projective thing. So what you essentially you are talking about taking away the scale. So you want a projective thing. So you want a ratio of stuff.
Right.
That's basically what you want.
Okay, so you must go on, but usually I think of 2 complex coordinates, right? And then I identify
No,
with
that is a bit. So here that's not.
That's not what's going on.
Not as a complex number.
Yeah.
Just real number.
I have real number.
Is a bit of a stretch.
Right.
Okay.
But it's best to stick to real case.
Mhm.
So in RD, D-dimensional space, the conformal group is SOD plus 1 comma 1.
Right.
Yes.
So it suggests that it must be linearly realized in D plus 1 comma 1.
Yes. Okay.
That's that.
That's right.
That
Yeah.
addition.
And so that's that.
And the way
addition
that's
of coordinates.
And the way
That's-
you get
that's-
the so you write is go to the null cone and identify the rate. So that gives you
So
the
that's how I should think.
yeah.
So
Okay.
P and Q are like, so P plus minus Q by Q or something in UV.
Okay. And now you identify. And normally you would have put a constraint like this is equal to 1 or something, but
That's what zero. So this is the null cone in 2 high
and
dimensions.
that's just identify the points that you see.
Yeah.
Or the entire manifold is.
No, but if you don't have the null cone, then you will not be able to identify the rays, right? Because that has to be.
So you have to raise takes you to the null cones actually. Raise is already about the null cone.
Okay.
Yeah.
Go ahead, yeah. Okay, thank you.
Yeah, that's basically some.
Sorry, what is the down map doing?
Which one?
The lower one, 5x.
Oh, I have gone from here, embedded it somewhere in a bigger manifold. Have to come back. So this is a projection.
What is the operation exactly?
This one, x goes to x by v. Yes.
Yeah, but like, can you tell me in terms of the coordinates?
This is the coordinate. X is the coordinate. So I have X u v in the coordinate in the M sir. For non-zero v's, I take the ratio X by V.
You mean mod x square by v?
X by V, then mod X squared by V.
Oh,
Yeah.
The group you will obtain is SOP plus 1 Q plus 1 plus 1.
That's why it's homeomorphic to this.
That's
Yeah. Now, right. So this is the setup, and now as I said, conformal maps are angle preserving maps. And there's a theorem which goes back to Liouville in 1850 and generalized in 1937 by someone called Hantius. Says that only angle preserving maps of M are D, other sphere preserving maps, which are Mobius transformations on M, and there's a conformal group of M. Again, everyone knows this. I'll try to rewrite this in using Clifford. So let me just rewrite the definitions for once. So the components connected to the identity in this group are the translations. X goes to X plus Y for all Y. Orthogonal groups, rotations of this X's, scaling for non-zero, and as Abhijit said, for only positive ones here, real numbers. And this is what is called a special conformal transformation. This is a combination of the inversion, translation, inverse. So that we know.
I have a question. So in the Euclidean conformal group, there's generally two disconnected components. They're related by an inversion.
Yeah. So I have a plus here, and I'll bring in the other part later on.
So even for the PQ case,
Yeah.
which I'm not sure, are there two disjoint components?
Right. So for example, this is something we know. For M equal to R2, the complex plane, the double cover of the Mobius group is this, given by this. Z plus B is given. And that's in SA to C, you know that. And this is something I wanted to generalize. Typically, we write these things as orthogonal groups and all, but this way of writing this some kind of AZ plus B divided by CZ plus D has some advantage, which I'll try to impress on you. And that's the reason I want to rewrite all these things in terms of Clifford.
This is in 2 dimension, but now you want to do a similar thing.
Exactly similar thing. I want to basically mimic this whole thing. So for that, I need some mathematical formalism where I can do this. So that's what takes me to this formulation in terms of Clifford algebras.
And can it true for D greater than equal to 2 or D greater than?
Oh, no, this is only for D greater than 2. For D equal to 2, you know that conformal group is much bigger. You have any analytic transformation is part of conformal group. Yeah, so very brief introduction to simply the jargons. So a Clifford algebra typically denoted with 2 numbers, PQ, the same PQ as I wrote down earlier, is a D-dimensional vector space spanned by an orthogonal basis. That is, I take E mu's as the basis elements, and they are 0, the dot product is 0 if they're not equal, and if they're equal, then I have a square of E nu, which I identify with the same quadratic form that I wrote here. So some signs sign the signature, some are plus, some are minus signs. There's a standard way of defining a Clifford algebra. Then so start with this. So this is a D-dimensional vector space of E's with this property. A Clifford algebra is made up of tensors out of this. So it essentially means multiplication of so it will be like E1, E2, etc. of En to V. And E's are taken to satisfy this extra condition. This standard thing.
So sorry to be so dumb, but the only place I've encountered Clifford algebra is gamma matrices. And gamma matrices satisfy the second.
Gamma matrices is choosing a basis of that. I'm just writing gamma.
What's the analog of E dot E nu prime equal to 0? Some trace.
Yeah. Thank you. Yeah, I'll come to that. So yeah, so Sandeep says, let's think in terms of gamma matrices if you want. And a general element is the last part. Oh, these are dimension calculations.
How are we getting that dimension of?
dimension of this thing is all tensors that you can make out of this up to D, right?
I see.
And with this, there will be an anti-commutation, so it's only symmetric ones.
So it will be
D choose R.
because if you have plus sign, then you.
That's it. So it's the same calculation as gamma matrix calculation to the power D.
E nu by C prime with C2, that dot, is that just matrix multiplication? Or
Give me 1 minute. I'll come. Yeah. So the dot has to be for a vector space. I know what dot is. That's not a problem. For these particular cases, one has to define better. Right. So general Clifford algebra element is written like this, and okay, yeah, so fine. So a bunch of E's juxtaposed together, and one adds an extra element E0 equal to 1, like gamma 0 that we do. And now again, this is a slightly abstract way of writing it. There are three involutions in this Clifford algebra actually. One is simply changing the sign of the immus. One is in a pattern like this, transpose. So E nu 1 to nu k goes to nu k to nu 1. And their combinations can be used. So first a row, this is called inversion or reversion sometimes in this literature, and then take a transpose. And that defines something called a bar for you. For one E nu, its E nu 1 is minus image. Now, norm square of an element is defined as this. This is the dot product. This gives you the dot product actually. And the trace of this gives you the zeroth component. And yeah, so if you don't have to remember almost anything here, only thing to remember here is that I can actually define something like a bar here, like the gamma matrices, and I have a way of writing the dot product. So the quadratic form is chi bar and chi bar chi.
How do you define the trace of?
If you want, what will work for me is that you just write down gamma matrices and take a trace in a basis.
But that just for like gamma matrix example.
This is-
In general, like,
you just define this as the map.
that is the definition. Define. We can use the earlier properties to show that.
So the meaning of what's asking is about the meaning of trace. Trace is a map from this to that. So one way of defining it is in terms of this. Take just this component. The other way is equivalent ways to take a trace if you know the matrix representation. So it's just a
gamma product.
that's a mathematician's way of writing stuff. Yeah. Yeah, but the reason I wanted
For the benefit of some of us, me particularly, please dumb it down if you don't mind as you.
yeah. Actually, the reason I do
This is good. Please go on.
In the last slide, you defined the dot as chi bar plus chi bar.
You see, this that's it. So chi bar plus chi bar chi.
That equation, the right hand side seems to be a matrix.
Yeah, there'll be an identity hanging there.
Yeah, so.
That's fine. I have defined E0 equal to 1.
Okay.
Hang on.
So I spaced out rho and tau are what again? Tau is a trace.
Oh, no, not trace. Tau is this transposition. So I have a bunch of E's sitting here, E1 to EK.
Yes.
Just reverse their order, EK to E1. And this, since they do not commute, this is going to give you something extra.
It's a sum map.
Sum map. And rho is reversion, simply changes the sign of the basic E's to minus. So for example, if I go E1 to K, I'll have a minus 1 to the power K. So if it's even number, I have 1. If it's odd number, I have minus 1. There are other implications. People use it in Clifford algebra literature. I'm not going to do that. This is actually related to the spin set sector that we got. Exactly like the gamma matrix things. But I'll not get into spin and all.
So should I think of this as a matrices and some dimensional space, the way we describe with gamma matrices, or just symbols?
No, if you want to choose a basis, and that's this next slide here. If you let me just make these statements and yeah, so it'll be clear.
Sorry, one last thing. How is the real number chi bar chi? The non-square. Chi and
So I have defined chi
those
bar.
are tuples and now.
I think you have that rule, right?
Yeah.
Inu prime is
Zero. And so it's a inu. So you have to use this like we do gammametry stress calculations, right? It's the same thing. Gammametry. Yeah. So with this, let me just make this statement and then I'll connect it to the rest of the thing. These usual things. So So I want to write this in terms of this Clifford elements for some reason. So let's consider this. I'm in RD. So I put one of the signatures to 0. So I have Clifford D minus 1. And then I have E1 to E D minus 1. D minus 1 of them in the Clifford algebra. I have added E0. So I write the d-dimensional coordinates like this. Compare this this is something we are all familiar with. We write 4-dimensional coordinates in terms of Pauli matrices like this. And indeed, these Pauli matrices can be thought of as quaternions, which are special cases, 4-dimensional cases of Clifford algebras. So it's basically a generalization of this thing people did 100 years back to write the. So this is how you write Euclidean, or actually in principle you can write RPQ, but we'll talk about this. So this is how you relate the geometry to the algebra of the gamma matrices. And then it's clear what using this, I have x dot x equal to the same quadratic form here for these x's. When I write this as x bar plus x bar x by 2 and so on and so forth. X inverse is defined as this x bar.
So x. Let's just think of this as a matrix.
Yeah.
Right. So x dot x means what? I take two matrices, take product, and then take trace.
And trace is defined like this: x plus x bar. Now, in this line.
Is inverse a verified operation in algebra, in this Clifford algebra?
Unless this is 0.
Is that a matrix inverse?
Which one?
That x inverse.
Yeah, of course.
It's a matrix.
If you are in the matrix representation, it's a matrix. And that's precisely what I need. That's the. I'll try to convince you that this is I needed this.
So sorry, x bar was for sigma I is minus sigma I.
Yeah.
And sigma 0 goes to sigma 0.
This is confusing. Sorry, the last equation. I mean, trace x. That means it's a number, right? But on the right hand side, it's still a matrix.
No, it's trace x will basically give you this. So other things will change as fine here. So this is
no, but I'm
x.
just thinking of x as a matrix now, right? Because x, just think of that. Just take this example. If this is a 2 by 2 matrix, 2 by 2 matrix, this is 2 by 2.
I know.
Right?
Yeah.
So now trace x is a number, but this is a matrix.
This is the way of writing things. Yeah. So if you wanted a
So how do I get a number from here?
just remove the E0. Remove the E0 from there.
I see.
So that's the way of mathematics. I mean, that's how they write this. That's why it's called it a map. And there's a by. That's why it's a by 2 there also. There's a by 2 also. Yeah. So you can use it that here.
So in the previous slide, are you allowing all linear combinations or only symmetric linear combinations, anti-symmetric also?
Here,
Yes.
Everything.
You want to know. Oh.
this guy, yeah, everything is allowed, depending on what you want to do. But now this is a very general. I don't need that. Here I need only these things, right? Only is there.
Oh, here it is.
It doesn't matter. Now you define something called a Clifford group out of some particular elements. You see, as someone was asking, that some of it with x is multiplied. Some of these are invertible if this mod x square is not 0, which is to say basically that unless it's a null vector, I can invert it. So take the invertible elements, the vectors of the Clifford group here, and they form a multiplicative subgroup. From there you define, at the moment, let me not get into that. It's a particular way of, so basically it says that you start with an x, you multiply it with q inverse with a slightly changed version of the reverse version of q, and it still has to be. So it's basically a closure relation using the invertible elements here. And this gives you a group. You can check that. This has a group properties. This is called a Clifford group. Out of this group, now you take this matrices. So A, B, C, D are from this group, this that I form out of this Clifford algebras with a certain conditions. But if you look at it with tau, if you ignore the taus, you see that it's basically like AD minus BC equal to 1. So that's like our good old modular groups. Then this is called a Mellin matrices, and they form what is called a Mellin group, denoted as gamma D. Sorry, SL2 on gamma D. So I have 2 by 2 matrix, 2 by 2. Gamma D is this guy. So it's basically a closure relation. It tells me that if I do a similarity transformation on these vectors that I define, I'm in the same space.
So, sorry, but it would be some subgroup of the gamma matrices or products of gammas or something. Sorry, what is?
Yeah.
And that's what it is. Take the gammas, take all products.
You see, this is slightly more than that in the sense that now I'm talking about Clifford groups on RDs.
Yeah.
And now have X. So it's basically these guys rather than just gamma matrices.
Okay.
So I'm saying that you take X from here, multiply by, and do a similarity transformation, ignore the rows now. And I still have to be in the same RD. It is a kind of closure relation.
Among those
X's.
with the E zeros added.
That has to be there. I mean, that's a kind of a nicety condition of this.
But that defines a sub.
That different sum, multiplicative sum. I needed a multiplication. And out of this, I form now 2 by 2 matrices. So these elements of these are from this group.
So how does this gamma looks like it's a set of X's within RD, right?
Right.
So some subset in RD. How does this RD subset look like?
That's what I'm saying. So
No, in physical space now.
no,
These are all some physical space, right? RD.
these are all elements Q which are invertible,
Yeah.
such that they preserve the X's in the same group.
Yeah.
So whatever it looks like,
So isn't that it rules out only the origin of art?
more or less. But yeah, there will be some subtleties later on. Because you see, these are all defined with PQs, so there'll be more. I'm just
So in PQ,
downgrading it to only Euclidean stuff.
in PQ it also looks
Yeah.
some like
Yeah,
tools,
that exactly. I don't want to change the definition just because I'm downgrading. I just take their definition, use it for that purpose. It might actually simplify for RD.
And in that closure relation.
I'm saying closure in the sense that, so this is like all the Qs that takes your coordinate in RD and takes to another point in RD.
There an easy way to say why there is a row.
This is that, no, I don't have an easy way to say that here.
What was row at?
Row was this.
90.
This basically will keep the, this basically has to do with the fact that I have to keep the orientation on intact. Otherwise, the determinant will change, the orientation will change. Yeah, so one has this from and from this 2 by 2 stuff out of these gamma D elements. For D equal to 1, you can check that this gives you our good old SL2R. For D equal to 2, it gives us good old SL2C. For 4, it gives SL2H, H being the space of quaternions. These are
the global conformal groups in whatever D.
That's it. I can always write. So this is the SL2D. So as I said, these are SL2D is a double cover of the oriented Mobius group. Double cover because I can change the sign of all of this. Same standard stuff.
By Mobius, we just mean the conformal.
That's right.
So in D equal to 3, I mean, I'm familiar with R, C, and H. What would be a similar thing in D equal to 3?
I think it's some kind of SL2H restriction. Because of the gamma matrix problem that U is the same gamma matrix as the one. So this is in some sense a better, so general way of writing things. I just get these examples, understand that. So now let me try to justify why I used all this fancy stuff. This is what happened. Under this Mellin group that I talked about, this SL2 gamma D, this is how things transform. X goes to X, AX plus B, CX plus D inverse. Very much like the Mobius transformation that we are used to. X, I, J, the difference between them transforms like this with a tau here, the tau transposition here. But exactly like what happens in a Mobius otherwise. Tau I inlet because I'm multiplying stuff, so I have to reorder stuff. We know that in gamma algebra we have to do that. Determinant of, so this is mod square, of course, if it's this mod square, it goes as this. You can check that the volume form in D dimension goes exactly like this, exactly as in the Mobius transform. And for later use, I have defined this quantity, chi with 4 indices. So Ij, Ik inverse, Kl, Jl inverse, and you can check that the mod square goes as this, and this is actually an invariant of this transform. They're exactly like the cross ratios. Again, the reason I want it in this particular form is, apart from some curiosities, this -1s here. As I try to show that this is going to play some very important role in what I'm going to talk about, that there's a way of writing it in a form like the usual Mobius transformation in 2 dimensions with transformation going. So these are like covariance of this with kind of weights -1, depending on what you call weights, weight 1 or -1.
Sorry, what was the ABC? That group.
Yeah.
And
Same as that.
I'm just trying to see the counting.
Counting will match. Counting will match. You have to be slightly careful with this thing, but counting will match.
So you will get the dimension.
Yeah. Those things will match. Yeah, those things will match.
This SL2R, of course, is very easy.
Yeah.
ABCD.
That's what I said. So you have to be slightly careful with these tau's and all here. But yeah, it will match.
Some generalization of Mobius transformations, but for your Clifford algebra.
Yes. For
For
RD, for RPQ actually.
For RDQ, okay, but you mapped RDQ to first this Clifford group.
No, RD was rewritten in terms of Clifford algebra elements.
Okay. So
And then I have something called the Clifford group.
Ah.
And then it's exactly the same way that I make a transformation. X goes to this now.
No, so what I meant was you mapped RD to first a Clifford group. Then you define everything on elements of that
That's
group, right?
Yeah.
And so it's like, in that sense, a generalization of Mobius transformations.
This is
but
a generalization
for
of Mobius.
the Clifford
Exactly.
group. Interesting.
Yeah. In fact, the first time I saw this statement about Hansius that integrated into all conformal transformations and Mobius, I was curious in the sense that, I mean, how do you talk about Mobius for a vectors? And it turns out that this is what they were doing. They knew all this. Yeah. So now that's more or less the end of this torture on Clifford algebra. Only thing to remember is that I'll need this once later on. So I'll collect this. Tau. This thing, so reordering of this. Because you see, once you have inverses and all, it's not a simply one element, there will be multiplication, so there will be many things. Is sitting there.
And you do all this, but you have only one invariant cross ratio under ordinary Mobius transformations. So D or whatever, you get that all through the matrices. All nice.
That's this. Yeah. Only thing I had to do is rewrite this carefully. I have to order this properly. IJ, then IK, then K, then this. But one can do that.
So if you don't order properly, then it will not be embedded.
Yeah, because there's a discount. So I was slightly careful in ordering. Of course, I mean, we are talking about non-commutative stuff. But in the end, all I need is this. And this also, okay, by the way, so these Cliffords directly go over to the spin groups, we know that. So in principle, I can incorporate spins as well. I have not done that yet.
Sorry, somewhat tangential question. There is something people talk about, right, which is a Q-deformed symmetry, right? Sometimes people talk about this SL2R, there is a Q-deformed SL2R and so on. Does that framework fit well in this?
Q deformation, if I remember, was changing the commutation relations, right?
Yeah.
So,
L0 L plus is
AB is something like Q BA, right? I mean, sorry.
Yeah.
Something like this equal to some stuff. So this changing the commutation relation here. As it is, I don't think that has to do with Clifford algebra. So it's only +-1 that goes over there, and then one knows that you write Clifford algebra. This is a way of rewriting our spin groups and pin groups.
Okay.
Yeah.
I mean, in solving these questions about Bootstrap, one important strategy
would have been to go over to Q
is
deformation.
to be able to truncate the equations in some convenient way.
Yeah, sure.
And people do that usually by taking, look at some derivatives, and then that's how we solve the Bootstrap equations and approximation. But if
I'll try to impress on you that I have another way of doing this using all this.
way of truncating,
Right.
truncating or something like that.
So that's right. Yeah.
So this in the spirit, let me ask a question which is
How
so
much
far above my
time?
pay grade, but
Very bad. Yeah. Okay,
Another way of truncating that our friends across the corridor use is they go to p-adic numbers. Sorry, but is there an analog there where you do p-adic conformal?
No, there is a p-adic version.
It's a nonsense
But
question.
there's a problem. No. I tell you, sir. This is not related to this.
Some limit become ordinary.
So that's the adelic limit. Yeah.
So what limit? Sorry.
An adelic limit.
Okay, I'm happy to withdraw the question. It's nonsensical.
Adelic limit. Yeah. But this is something very interesting. You see, if you remember, for p-adic numbers, you have this property that any triangle is has two sides equal, right? This is the property of that ultrametry. And now there's a problem. So the point is, now what happens is, now if you write down these cross ratios, they can be 1, 0, and infinity.
So it's some drastic.
It's very two drastic things. Unless you somehow say that I change OP somehow, which I have no intuition about, people have not done that. You might as well say that because now you don't have the problem of 2 points coming together and giving the same of the stuff. So why not change OP? But I will get into that. But here the problem is that this becomes very drastic. Yeah.
Sorry.
Yeah. So now, okay. So let me just go over. Again, this is something everyone knows, but I just wanted to reiterate once. So this is what about representations of a group. So now I have a group, conformal group that I have written in terms of Clifford and all, and I want a representation of this. So what is the representation? You start with a geometric action of a group on a manifold. So you basically have an order pair. So a group here and a manifold here. Take this element and it takes you to the manifold. So the geometric action, you want to lift it to the representation basically is lifting the geometric action of a group on some kind of good functions that you define and make it covariant under it. That's the whole that's what we have done. So this is a fancy way of writing this. So I have functions on this manifold and I want to lift it by this. So I first take the action of the group, take x to gx, and then want to lift it, and this is the condition that gives me the representation. So the RG on the function fx is given by first take gx, then map there, and perhaps you are allowed to have a factor here in such a way that RG G prime for two group elements is a product of RG prime.
Let me just make sure I understand. So you started, of course, with your manifold.
Yeah.
Then you associated a group with it, the Clifford group.
That's a conformal group.
Which is the conformal group, but you went through this Clifford group, right?
Yeah.
And then functions of the points on that manifold will become functions on group space. Is that right? I mean, that's the lift, right?
That is the lift, but that
M goes to M, then up is.
Yes. So you can say it in that fashion. Yeah.
And then and then the action. And then you want functions valued in this map, which will transform nicely.
Right. Yeah, this good has to be defined. That's what
good is to be defined as
But,
representation.
Yeah. So the standard thing. Now, as we said, that the correlation functions are representations of the conformal group. That's what we started with. Now, I can now look for have n points here on the manifold M, and these for the correlation functions, there are two ways to go about it. One is to take tensor products of representations of the single particle irreducible representations of G on M, or you go over to representations of G directly on the configuration space of n mark points on it. And I'm going to take the second route. So I'm looking at functions on the configuration space of n mark points in the manifold.
This is because in the end, you're interested in the correlation functions, which are like at mark points.
Mark points.
It seems like the natural.
So I'll not talk about any operators here. If you remember, I started with a group. I never wrote down the algebra. So I'm looking at only the correlation functions, and they have.
The information of the operator will be in this alpha.
It's all in there. I'm saying that I'll not talk about it here. For my purpose, it's just a representation of this is good.
And you will get some scaling weights outside, right?
Yeah. Or only say I will not identify the operator.
Yeah.
That will require dealing with the algebra part, which I'm skipping.
Yeah.
So are these mark points fixed?
No, mark points can go around.
They can go around.
Mark point means they're just mark. Only constant typically is that they don't go on this. I'll talk about it in the next slide.
And also identification, right?
might be there. And that depends on whether you want to do it or not. Okay. Yeah, whether it's identical or
For
not.
identical operators.
So so this is a matter of definition, what you call a configuration. But some people call it after the permutation, some people will call it a configuration space before the permutation. I think they also have different names for this here.
We're still considering the full group along with inversion.
So now, for the configuration space, I have only a few things to say. So when you talk about the configuration space has to be big. So one has to choose something called a model. So the problem with configuration spaces is the following. So if you have two mark points and they are going around, there's going to be a problem when these 2 points collide. And that gives you a singular problem. So many of us have actually done this for this double pendulum, etc. The kind of configuration spaces you have in BSc, if you remember. But now, so what you do, so there's a very nice intuitive way of thinking about it in this paper of Fulton and McPherson themselves. So what they say is that, so the 2 points are coming and colliding. Think of these as 2 particles coming and colliding. So when can this happen? This can happen if and only if their velocities are exact and opposite. Right? Otherwise, they will come and stop. So if that happens, then you go to, so when this happens, look into the acceleration of these guys. The velocities are the same. Look into the acceleration. If the acceleration is also same, go over to the next third derivative and so on and so forth. So this way, you can actually distinguish or stratify points depending on up to what derivatives in space. So think of acceleration, etc. as some derivative, some energy derivative of xt, the position, and classify these points according to up to what derivative they go to 0. Okay, that's a very nice way of doing that. And once you have classified them, then so you bring in the singular points, and so that's what is called a group. The grouping there is called a stratification in their language. So Fulton-McPherson proves that you start. The mathematical statement is this: you start with this diagonal where the two of the mark points are paired by 0 and blow them up. That's all, and that takes care of all of this singularities.
Isn't the natural way to resolve things, at least in complex geometry, to blow up?
Yeah,
you just keep the directions. And
the
you
problem
put a P1 every time. This is at least what we do in algebraic.
That's right. So
you don't want to do that here.
No, you do that. No, you are doing that here. But point is, as I said, so once you see, when you blow up, as I said, so when the velocities are equal and opposite, you are looking at the tangent space of this configuration space. Who told you that this blowing up the tangent space is good enough for all orders? So that's where Fulton-McPherson comes in, and it's a big paper. It's a famous paper. That's why they are famous. They prove that blowing up is good enough.
But maybe a more general notion of blowing up, right?
No, this
It's the
same blowing up. So 2 points are coming.
Directions, you are keeping higher derivatives.
This is the importance of that paper.
So it seems like normally I think of blow-ups as I just keep the direction.
Right.
So you identify.
So this is the same thing because you take ratios. What you do essentially is put in meromorphic functions instead of just analytic functions in this in the ring of in the algebraic geometry language. In the ring of functions, you bring in meromorphic functions, and they are saying that that's good enough. You don't have to do anything else. That will take care of higher order singularities as well. Anyway,
I thought we wanted to get some configuration space which avoids coincidences.
And then you will see that it's a badly singular, so you have to desingularize it. It's again the same thing like putting the for the complex plane, bringing the infinity in and declare it is a good point.
But don't you have to avoid when just the relative distance is 0? Why are you looking at velocities?
Sorry? No. So think of these 2 points coming on the. Yes. So they have to first be on the same line, right?
Yes.
So that's essentially the tangent of that configuration space.
But can't I just delete the points where
you can delete it, but it's a badly singular point. This is it's the same thing as exactly the same thing again as a complex space. That you have a complex plane. Why do you want to make it a sphere? The reason is that because there's a point called infinity, which essentially means if I talk about sequences in this plane, things will not converge. Then what I say, declare is that I'll say that, okay, infinity is a good point in my space and things will converge. That's the whole idea. So do the same thing out here. And okay, this is what they do. That Fulton-McPherson, so this is the configuration space if you want, where you have m to the power n mark points here, and delete the, as you say, the points which are pairwise equal.
Yes.
Right? So that this is a badly singular space. So these are n non-coalescing points on this. Then you, to compactify again, anytime you want to make it a complete or compact, you embed it in a bigger space, like we did it just now for the conformal thing. So this there's a theorem which shows that this completion is embedded in this space, where I have m to the power n for n number of mark points. There will be these many spheres of d minus 1 dimensions, and there's an interval whose raised to the power this. Given these are the coordinates of this. So x1 to xn, of course, are for mn. The spheres are given by these guys. Xi minus xj by this. Clearly, the mod of them are 1, so they form a sphere. And thirdly, you have these quantities aijk defined as xij by xik, mod of them. Okay.
So the sphere is exactly those P1s.
Exactly those P1s.
But you have something more to take care of three
Yes.
things coming
Three
together.
things coming together.
This is a very new thing.
That's the new thing. That's what topologists have done. In fact, now this is a point, and let me mention why I don't want, why I didn't talk about Lorentzian signature stuff. I don't have this theorem because there is light cone there. So other than that, if you look at the calculations that I'll be doing, it seems everything goes through. But I didn't claim anything because I don't have the protection of this theorem. Okay.
So the theorem is what? CNM has singular points.
CNM will have singular points. It says that I have to desingularize it by a complex completion of this or compactification of this by embedding into this higher dimensional space.
And you what are you calling that manifold?
They don't have a name actually. So it's okay. You can call it a Fulton-McPherson complex completion of this configuration space. That kind of. So this is called, they called it, people, it is called a model of the space. There are other models. There's another called Hilbert scheme. There's another third model called wonderful compactification. It takes more the group theoretic stuff into account. But
Solutions will be important. Or
which one?
maybe the way to understand this stuff.
So this is the point. So basically, I have now these things. So if with this statement, now the functions I look for. So for the representation, I needed functions on this configuration space. So now I know from this the coordinates of my functions. The coordinates of the functions are xi, vij, and aij. Right?
So one question, I mean, how is it that, so this is, you're saying it's a tensor product, this configuration, is it embeddable in that? Or?
Yeah.
So what is the dimension? First of all,
This is very high dimensional space, right?
and the configuration space dimension.
This is embedded. This is not identity. See, this is like going to, instead of 2 higher dimension for conformal compactification, going to very high dimension.
Okay, but this dimension is this RD to the power n, right?
Dimension is the same, but you are embedding it here. So the only thing I learned from here is that when I'm looking for representation, so my conformal group in this space, my function is going to be a function of these coordinates. Nothing it can have, and it cannot have anything else. Right? Out of this, xi's as themselves are out because I want translation invariance. So only differences can come in. And I'm talking about scalars, only mod of the differences will come.
So can you just tell me what is Vij and Aij? Vij is relative distance.
Normalized. Aij is this ratio. And you see this can go to 0 or infinity depending on which one you do.
Why do you have to write AIGK further? Because the mod is already there, right?
Which one?
So in the next slide, you said that function should be of mod xij.
Yeah. But on the other hand, this particular combination, I just wanted to mention the particular combination.
But what is, I mean, if you,
This is going to be a function of this, but only xij's themselves and this particular combination of xij by xik can come in.
no, but if once you say, if I forget about AIK, if I just say that f is going to be
Yeah, if you are happy with that,
mod xij,
sorry.
that's it. Right? So that's, I mean, that's a familiar statement, right?
That's a familiar statement. Only thing is that, so let me just mention that the way place I'll be using this is for cross ratios. You see that cross ratios are IJ, KL, IK,
Yeah.
JL. So these are as two A's basically. That's why I wanted to be there. Two A's.
Yeah.
You multiply, and
But
you can check the numbers of set.
Is it that the conclusion will be that the correlation function should be a function of cross ratios times some weight factor? Okay, fine.
Coming from, so I'm saying that I needed this because I'm not doing the standard stuff. I'm looking at for the representation in this very weird space. So I needed all this protection. That there's nothing, because before this, I couldn't actually say much about the configuration spaces, right? I mean, they have told me that this is the coordinate, so I just use it. And I see that this is a match with whatever we do.
BIG is the angle at which the INJ.
Right. So,
Sorry, in the last slide, AIJK, let's say IJK is 1, 2, 3. If A1, 2, 3 appears, does A1, 3, 2 will also appear?
it can appear, but there'll be relations among them. That's clear.
But from the earlier like that you have, if A1, 2, 3 appears, A1, 3, 2 will not appear, right? Because you're taking.
That's what I'm saying. So if you consider a space of AIJKs, there'll be relations. So you can find out the independent ones. This is written a basis, but you can change it depending on what you want.
My problem was that Xij is appearing in the numerator, right?
Yeah.
So there's some this priority of J over K,
Sure. Yeah, it's fine.
but it should not be, right?
That's what I said. So
because
so there'll be relations which will take care of that.
okay.
In fact, that's how you embed it anyway. So now, going over, so under the conformal group, this is the geometric action. And as Abhijit says, I have done all this to come to the usual match with whatever the usual results are. That this is the transformation, and this gives me the representation which I am going to use for the correlation function.
And these X's are now
X's are standard.
standard.
The standard X's, but I mean, see, after I have written a mod, it doesn't really matter. Mod comes from the determinant in the Clifford algebra and standard quadratic form in the geometry, right?
Okay.
Yeah. So now let's over to G's. So as we know, this is a trivial statement. Covariance under the conformal group already fixes the 2-point and 3-point correlation functions like this. This one can fix, and here the 3-point function OP constant arises in this particular way, and as Sunil pointed out, I had a typo in the first page. It goes in the denominator. Yeah, but now to the 4-point. 4-point has problems. 4 points has this conformal invariance of cross ratios. The way to handle those is this. So you have n-point correlation function here. You pass this by using projections in between. So just plug in projections here, and this is the projection operator. I have two phi's here at different points. I have a weight factor kernel here and then integrate over 2. Now, this is not the very standard way of writing is. In standard way of writing it is like this, and this at x and phi same x, but a shadow of this here. So if you look at the definition of this shadow, it's like if I integrated x prime here, I'll get the shadow of phi. Essentially, is that.
I should know this, that this is phi delta as a resolution of identity in some
Yes, so this is the property.
phi delta.
You can check that.
So it's a projection, and moreover, it is equal to, the reason you can insert it is that it's equal to identity.
Yeah, sum over delta. Yeah. Sum over with the sum over
With
delta.
the sum over delta.
Yeah, of course.
But this is, of course, then this, I mean, in the beginning, Koushik said that it's not going to consider spin.
That's right.
I mean, if you do have spin, then of course some more delta.
Some that's exactly.
Be left over fields there.
Yeah.
But if with the assumption that there is no spin, then yeah.
Right. Without any spin, this is what.
If there is spin, you put in the delta S also.
Yeah.
Some
Else will come.
Okay.
Yeah.
So I think never mind the word sum over that. We should sum over that.
Yeah. This is sum over delta. Yeah.
I don't know.
I forgot to put it. Yeah, I have put it here. Yeah, the next page. Yeah. Right. So, for example, if you have an endpoint correlation function, you can do it this way. So, first put a projector after two of them. You have get a 3-point correlator here and the rest here, and keep on doing this. For 4-point, therefore, if I have 4 points, this will suffice. These are going to be 2 3-point functions. This will break into 2 3-point functions, right? Like this. So the 4-point after putting in the projection breaks like this. 2 3-point functions, which we already know from here.
There's a C in this.
Right?
Should be C, right? 3-point function is a function. Or is it there? Yeah, that's C, yeah.
Yeah.
No, I mean, in the integral.
But he has not plugged.
Okay.
Here.
Oh, that C is in there. Okay.
Yeah. That's it. Yeah. So what is it? So I have to do these integrals. Now, if you just massage these integrals, etc., one can actually. So what one does is you put in the 3-point functions with these particular weights and these particular positions, and massage the integrals a little bit. You can do some of the integrals and some not. You rewrite this in this fashion. So in the so-called S channel, you have 2 C's sitting here coming from the two G's. You have this so-called leg factors here and a symbol here. I'm going to explain the next slide. And similarly, just do a 2 to 4 exchange to get a T channel, like I showed earlier, and you get another expression, a similar expression, and the bootstrap equation is equating them.
Yeah, but now coming back to perhaps one of your motivations, when you try to actually do those integrals, you get singularities. Right?
Yes.
So you have somehow resolved that.
Yeah. So this is how I define this. This I has some indices here and positions here. This is the definition of I's.
I see.
So I have not done the integral. So I said that you massage the integral and rewrite in this particular form, take out the leg factor and put everything else in one package like this. And it has interesting properties. If you look at it, you will see that this indices sum up to D.
So just one question. I mean, when you do this type of integral, what you get, people call that sometimes conformal partial wave, right?
This is conformal
as
partial
opposed to
wave.
conformal block.
Yeah.
Because it has
Delta sum.
the OP limit, it has 2 types of behavior, x to the power delta and d minus delta. So this is a linear combination.
This will generally be a linear combination of that. If you could evaluate the
Yeah.
integral, this is what is going to happen.
But in at least in standard Bootstrap program, you want to put a particular conformal, particular behavior.
Right. So that will be, that is typically done by doing a OP consistency. You assume that whoever, there depends on whoever are coming closer earlier. I'll use that. So, yeah. So far I have not done that, but yeah.
Sorry, sum over delta is over the primaries.
Sum over delta is over the primaries here.
But a priori, do we know that what are the primaries if we don't know the CLP?
No. I'm saying that if we are summing over only primaries, because I have not committed to a particular CFT yet. I want to keep it as general as possible and then see how much I can talk about, how much I can talk about the properties of data.
So this expression is general. Like,
This expression is so far general. I'm not committed to any particular here. Right. So now, okay, one interesting thing is that this, as I said, the sum of these indices, what I call mu here, denoted by mu here is D. And this is an identity. It's very easy to prove for complex numbers, as you can see. And you can prove it using the Clifford representation of vectors here. That's another place I need the Clifford. It's easy. Otherwise, it's very difficult to prove this identity actually. Because I don't have something like an inverse, etc. So I have to give a meaning to all that. This identity becomes kind of, it doesn't look like this at all. But then something very interesting happens. I don't want to evaluate this integral. I want to write a differential equation for this integral and solve it. The integral evaluation is always difficult. You can check by if you are allowed to take derivatives with respect to the xi's here within the integral side. You can check that this satisfies this differential, second order differential equation. Again, these are the Clifford elements. again, I tried it. It's very difficult to get this equation otherwise. If I didn't know this connection. It does. And on the other hand, for it was complex numbers, you do it in just 2 lines. Very easy. So I was looking for this, generalizing this without this whole technology of clippers, I couldn't do this. And now I can go back and rewrite it, but I couldn't actually derive it in this form.
But the theorem itself has the algebra in, right?
That's what I'm saying. So once I do this, now I can get rid of these. I mean, I rewrite this without ease. But I couldn't really derive it in this kind of form, in a nice form, without knowing this. I tried that. So that's part of the reason one had to go through this report stuff.
Sorry, I mean, this type of integral, I mean, the one that you wrote in the earlier slide, where you have this kind of structure, right? Where you have that gluing this.
Yeah.
This exchange diagram type structure. And that integral that you get, I mean, usually one writes a differential equation for it by specifying that the conformal Casimir is delta times delta minus d, right?
That's right.
So that's another way of getting differential equation. Is that the same differential equation?
That's right. For 4 points, you check. So one has to. So you have ease here. So you have to take a trace and you get that equation.
Okay.
That's one thing. But I have a guess. I have not been able to prove it. I've checked it for, of course, in lower dimensions. But I think for even 4 dimension it works. I am not talking about in terms of algebra. I'm talking about the group stuff. So I have not used the Casimir. But still, I'm getting the same because there must be a reason. It looks like that what one is actually handling with all this here is all Casimirs. You are in the same differential D module and you are actually using all Casimirs. But I couldn't prove it in general. I have not checked it for all Casimirs in D dimensions. But in low dimension is one. Yeah, I don't know whether it's useful or not, but it's there. Yeah, so now if you check this, it's easy to check using this formula that I wrote down for under this conformal transformation of this xi minus xj, etc. stuff in an earlier slide. You can check that this I mu also transforms like this with this mu sitting here. So this also is a representation of the conformal. So I can use the same on such like
just to ask you, is some very clever thing happening in that? To begin with, the integral is singular and so on, but somehow casting it as matrices and all this is implicitly choosing a way to regularize it or
no, that's not.
It's just identity between 2 singular.
So this is compare this with a standard integral way of writing hypergeometric series functions, Euler integral formula or Mellin bond, whatever you prefer, and write the differential equation for it. There will be points of degeneration and solution which will take care of this, right? But the point is, we'll know how to handle this through analytic continuation or whatever. Otherwise, it's very difficult to make sense of this integral.
One more comment is that sum over mu I is d. So those mu are smaller than d. So at the coincident point, there is not really a singular.
So yeah, that's right.
But probably you will get other powers, right?
Yeah, so this is so what
dimensions.
Yeah. So what happens is after I have taken out these guys, this is the conformal. So this is why it's called a conformal integral now.
Okay, but just to ask you, you always land in a situation where you have no divergences. I mean
divergences are here. Everything is here.
So the non
divergences are the leg factors. And there will be some divergences coming from the fact that the cross ratios are allowed to go to 0, etc., infinity 0. But that is part of the solution of this.
The integrals by themselves are never single, right? Given that all the mu's add up, given all the mu's add up to d or
depends. Yeah, that's so. Depends on. Suppose I take 3 or 4 of them, and maybe all of them going to the same point, and it goes up to d. So I have to keep myself, options open, right?
That's right.
Let's not commit to anything at the moment. Whenever singularities come, point is, I know this some representation of hypergeometric stuff, and I know how to handle.
No, but this seems much better. Somehow I thought that your view would be such that the integral is defined for generic points. Then, the next one are not on top.
Yeah, for distinct enough points, I think it's well defined.
For distinct points, it's very well defined. Although there is a slight problem here. I mean, I have written an RD here. I'm like doing a volume integral. There will be problems here at each point itself. One have to be very careful about it. That's part of the reason okay, that's why you can actually not evaluate this integral. You go through this differential equation because series solutions is better to handle in such situations.
Sorry, I have some maybe silly question, but the powers are 2 mu i's in the denominators.
That's because it's a mod square of this.
No, that's fine. But then the mu i's add up to e, not the 2 mu i's.
That's it. If you remember, at some point I gave the transformation of this. This goes as this thing lambda to the minus 2b. So that's why it cancels. In the measure, it's a 2d. You can check this explicitly for numbers, real or complex numbers. It will say that. This is that for there is clear that if I have a 1 x going to 1 over x, I'll have a 1 over x squared in the measure. So that's basically the scaling changes again.
Oh.
Yeah. So if you so if this is the conformal integral, and so now I want to also write this conformal integrals as we said as this, and this is going to be a function of this mod xi's and this invariance, which are written in terms of this as of which it said this notation was redundant. I just wanted to sort of mark this that I have cross ratio. The E is coming in. Now, going back to this observation. So now if I have a differential, take the trace of this, you get a very complicated second order differential equation. You can handle it if you want. But now there's an extra observation that we make. This is direct generalization of Mobius from numbers, complex numbers. And as we said earlier, the mod xi goes like this with the powers 1 here. These indices are 1 here. That was very important for me. And as I said, without Clifford formulation of this conformal group, I couldn't have written this in this particular form with -1 and -1 here because I need a determinant kind. So this it's a matrix kind of stuff that I needed here. So this is again a very crucial point here. So if I now what I do is I collect the indices. So xij transforms with the power 1 here for xi and the power 1 for xj. For the rest, it's 0. I just collect this in a matrix, which will look like something. I'll call it a curly A, and we'll talk about vectors, annihilators, so basically null vectors of this. So here's an example of how it looks like. So for n equal to 4, I have 6 pairs of ij's, 1, 2, 1, 3, etc. up to 3, 4. Now, x1, 2. So 1, 2 goes as cx1 plus d inverse, cx2 plus d inverse, 1, 2. So I write 1, 2 goes as cx2, 1 here, and 0 here. Similarly for the rest, 1, 3 has 1 in position 1, 1 in position 3, rest is 0. So I just collect that in a matrix. Okay. And these are the null vectors. Just write these as columns, these are null vectors of this matrix. These null vectors give you the cross ratios. So the way to read it is 1, 3 here and 2, 4 here in the numerator, 1, 3 and 2, 4, 1, 4 and 2, 3 in the denominator.
So sorry, I missed something. What is this again? This previous slide, I missed something. This is your
So in X, so Xij under this Clifford kind of transformation that I wrote down, transforms with Cxi with a 1 here, Cgxj with a 1 here, nothing else. And as I said, this was important. So the Clifford notation was important in writing this. So I collect it like this. So x1, 2 has 1 here in 1 and 2. This others are 0.
okay.
So it turns out that in conic geometry, this is like a Grassmann variety and so on and so forth. I will get into that. Now, clearly, since these are transformation rules, invariants are given out of this. Something that doesn't change. And so these are nothing but the null vectors of this A matrix.
So this is the calculation of independent cross ratios for n number of points.
No. Cross ratios on so far.
Not independent. Space is captured.
No, okay. It depends on what you.
Because 4 points you have 2, right?
4 points I have 2.
That's
But in higher numbers, it will be more. I'll get actually more than what I need for just conformals.
I'm sorry, let me ask you a question. I know I'm taking you back.
No,
But if those integrals are well behaved and generic, then isn't there some can't I be very simple minded and say open Grafton and Rishik or something and write them as hypergeometrics. And then it would make sense when they come together, fine,
Yeah.
that's
You
a
can.
standard problem.
You can, but in general, you cannot. In high dimensions.
In general, these integrals are unknown functions.
Right. So if you are in like 2 dimensions, for example,
Then it would be. But this is some generalization.
but on the other hand, it will not be there in. Actually, it will not be there in Grafton. You have to go to something like Iomoto, etc. People, but people are done.
But no, I'm just trying to understand from a down to earth motivation point of view. You're finally going to be able to evaluate these integrals or make sense.
Write down this as infinite series at least. Same as hypergeometric function.
Write them down in suitable infinite series. Okay.
And yeah, I'll soon come to that. I actually write down those expressions once. There's a horrendous expressions. But yeah, anyway. So these are the cross ratios that I get out of this null vectors of this. So this is some combinatorics. Now you choose I mu as this. So I have xij's taken out, and there's a invariant function of only the cross ratios here. I can choose these answers because I already know that it's I mu is a representation of the conformal group. It has only these coordinates, xij's and xi's. There's nothing else. And I've chosen some xi. Remember that if I do a row operation here, I get different xi's, but all of them are some functions of the original cross ratios. They're still invariant. Nothing changes. Now, and I have this is a notation that I write xi is as xij to the power this lij's. Lij's are being this size. This is just a notation for these vectors. And this invariant appears as Abhijit says that is a summand in the conformal block or the partial way. So it's exactly those. Now, and this if I make this choice, and I have to make connection with this is an answer. So you see that you have this, the Bij's are symmetric in the ij indices, Bii's are 0 because the xii do not appear. And with this matrix that I wrote down, with this matrix, you have this property that aibk is minus mu I is being the weights of this these mu's. Okay. And it was also known that BIs are not exactly unique. They can be, you can shift it by a multiples, any multiple of the null vector. But it turns out that the conformal integral is independent of them. You can prove it in general. So I'll not get into that, but yeah. Now, go back to this. So as I said, take trace of this, you get a differential equation. Now the observation is the following. Insert this ansatz in that equation. If you did that in that equation, massage it a little bit, you can rewrite the invariant part as a solution of this equation with this operator. Looks reasonably complicated, but I have defined theta as basically the derivatives, the cross ratios and so on and so forth. But this Lij can be broken into this form where I have a 4-index operator which looks like this. And then the final observation is that if I take this combination acting on where I have defined del ij as the derivative with respect to the mod square of xij, this implies, so this is a sufficient condition to satisfy this 4-index guy equal to 0, so that in turn tells me that Lij acting on I0 is 0 and so on and so forth. So this turns out to be a sufficient condition to solve my differential equation on I0. And what is this guy? This guy comes from here. This is the connection to the GKZ. This is what is starting with this matrix A that I wrote down earlier, and the L's being the null vectors. This is a system of equations called the GKZ, Gelfand, Kapranov, Zelevinsky equation. This is a generalized hypergeometric series. They have this property that A into this is the Euler derivative, Euler operator on I mu gives you the weights. There's no surprise here. This is how so this is always satisfied by our conformal integral. Second is this. So here what you do is you take this del ij's with lij's with positive L's here and negative L's here. So that means if I went back, so two of them are positive. So for example, del 1,3 and del 2,4 on one side and del 1,4 and del 2,3 on the other side. That's what you will do. So and that will give you operators of this kind. Exactly operators of this kind. And the observation is that these are sufficient conditions to satisfy my equations that I get out of my conformal entity. And yeah, so this is a condition. And this is example, interesting example. If for n equal to 2, A is like this 1 and 1, because 1 and 2 both transform this way, there's no null vector, and this tells me that this equation, so there's no null vector, so this equation is absent. Only the first equation is there, and it can only be solved for mu1 equal to mu2. And as we know that we actually have a delta mu1 mu2 for the 2-point correlation. So this comes up for n equal to 3 is the same thing. I have this matrix, so 1, 2 transforms like this, 1, 3 as this, and 2, 3 as this. There's no kernel, kernel is trivial. You write down the equations and you get this as a solution. Okay, so this is just a consistency check. Finally, for 4-point, again, this is the toric matrix rewritten. These are the xis, and there is some domain of convergence. I'll not get into the technicality of this, and these are the series that you get in certain domain of. So these are two variables thing, so you have a domain of convergence. So I have your for 4 points, you get 4 solutions, and where these xi1 and xi2 satisfy this condition, and you know that these are Apple functions. 4 solutions. I have 2 more on the next slide. Yeah. So 1, 2, 3, and 4. And these are 4 Apple functions. Two variable generalized hypergeometric sum. And if you go back, you can check that this is F4. F4 has exactly this discriminant locus.
So here you computed this integral, right? This
By as a series solution.
The series solution, and you got 4 solutions, but integral is some combination of that.
Integral is there. So this is that, and yeah. So one thing is, yeah.
Can I ask something? I'm sorry, I missed something. So we don't, to begin with, you have to evaluate a 4-point. You introduce this resolution of identity, which involves a sum over all delta. We don't know what values delta take. And finally, you got an answer. But that answer was what? For a particular delta in the
Yeah.
For a particular delta. Okay, got
I
it.
still have to give the sum to.
So for any particular delta, yeah, that's right. That's right. Sorry.
So these mu's have the delta. The mu's have the deltas.
I understand. Okay. Got it.
Yeah. So and there's a linear combination in general, but then if you chose OP consistency, we'll choose some of them. Part of them. You can impose this. In fact, we had a long fight with the referee about writing a fully permutation symmetric thing, which I think is going to be useless. But yeah, mathematicians want that.
So like in the series solution which you told about, so the the singularities in the integral will be in the same manner observed.
Yes, yeah. So for example, if you try to cross this from, you get a singularity.
Like
Like in hypergeometric functions, you have 0, 1, and infinity. It's a 2-variable thing, so you have a whole curve in the space of line 1, line 2. And of course, again, doing analytic continuation, etc. is very big.
So we missed this side-on-side relation. So side-on-side, I mean, if we have 4 points, there are 2 cross ratios. I thought side-on-side were those 2 cross ratios. So those are 3, right? What is this relation?
Oh, this is the convergence domain. So you have to be one side of this. This is called a data. So there's a way of calculating discriminant locus. You can calculate in Macaulay or etc. And it exactly gives you the discriminant locus comes in this form, but you just massage it and you get the usual. This is the standard convergence domain for Apple functions. In Apple, we write it in this fashion, but it's the same thing.
Convergence domain is not really a domain, but rather some sort of a.
So we have to be on one side of this curve in the two-dimensional space.
Just show those Apple functions again. There's some series expansion.
Yeah.
Right.
Yeah.
So presumably that converges
in this
in this.
Whenever this is less than 1, it converges. This is the form that I have written down. If you want to go to the other side, you have to do the analytic continuation. Those are known things. Those, as you said, can be looked upon from Grassmann or NIST. So you can write in principle, you can write a similar. So now I'm nearing the end, and I don't want to write any of these things. In fact, I don't want to use the series solution because there's a problem now. Now I want to use
Sorry,
this.
Koushik, sorry, excuse me. And this was for for a 4-point function in any dimension, right? So it's just a very general thing.
There's a D sitting here.
And some nice expression.
Yeah.
Got it. Okay, thank you.
Right. So now, so I'm going to write down, so take these solutions, put it in my G's, equate in the Bootstrap equation, want to do something with this. Now, clearly, this creates a big problem in the whole Bootstrap program. And because I have this size restricted in a domain. So Bootstrap equation is a function of two variables themselves. So Bootstrap equation has to be satisfied at every point in this domain, and that's the whole problem. So one considers, as Vijit says, by taking derivatives, etc., or take a functional, linear functional, and so on. Somehow you basically get rid of the dependence of the size. That's the whole idea. Do whatever you want. There's a beautiful way, which I'll try to connect to a little bit, done by Rajesh and Anindo using the Mellin space and connecting it to the Mellin diagram and so on. So that's another, by putting a particular type of weights. So that's another way of doing it. Here's another way of my simple way of.
Can we do with the four solutions that we got? Can we do with them independently?
No. So if you choose OP consistency, by the way, tells you that, for example, if I have this diagram, so 1 and 2 are coming together, it tells me that the leading behavior has to be x1, 2 going as delta 1 plus delta 2 minus delta here with a factor of 2, etc. But so it has to go like this. So if you want to choose that, you will choose, if you choose that, you will see that you will actually choose 2 out of these solutions.
And you are able to fix the seeds also, the relative.
Actually, we could permutation. My guess is that if I actually wrote out the whole series, it will be 0, like, because you were in some sense doing a permutation which is taking care of, taking care of both the channels and all. But the other referee wanted it, so we have to do it.
No, but what I'm asking is that can you from this solution get the exact conformal block?
Yeah.
So that is a particular.
That will be a particular
solution for frequency to see.
Always there will be 2 of them coming up.
I see, but also what is the value you can see?
Yeah, yeah, that's right. That could be it. Yeah. Now I'm not going to use that. So the whole problem is with the convergence of size. I want to try to make an integral out of this, do something, and it's going to create a problem. And there's a very serious issue. So what one does is, you first write this as a Mellin-Born integral over some kind of contour by extending it size to the complex domain. Then you have to make sure that there are certain branch cut, etc. that you have to take care of. And there are integrals. So there will be a sum over delta. There will be integrals, etc. And there's something like called Fubini's theorem that we have studied in BSc, that when can you swap integrals? And it violates, sometimes it violates those conditions. So swapping of integrals is not allowed. You have to be very careful about it. Richkov has a whole paper on that. So it creates a lot of problem. So I want to avoid this by using now what is called a GG system. GG system, as everybody asks, is very interesting. It was discovered by Gelfand and Graham. And they interestingly called it a GG system for Gauss and Grassmann.
An unusual case of academic humbleness.
That's right. In a very particular, let's say. Yeah. Right. So this is the thing. So you can actually show that this invariant part that I wrote down can actually be written like this as this integral, with a delta function sitting here. The integrals are some dummy variables Tij, which appear here with the null vectors sitting here, and Xi's are my cross ratios. This is something they have proved, and it actually satisfies some other equation, which including a difference equation. I'm not going to use that. But the point is, all I get from them is that this I0 that I wrote down has this representation, integral representation, and now it has a delta function and T. Now it's slightly, there's no, until I evaluate this integral, there's no restriction of Xi's. I want to use it to my advantage.
So, Schwinger,
This is
like you write here.
This is always the Schwinger representation. Because these are nothing but, you see, these are like point splitting actually. You are separating points from. It always appears like exactly like this. It's interesting. Yeah, it's very interesting and nice to map things like that. Right. So as I said, there have been a bunch of betas, and I mu was independent of betas, and so on and so forth. But let's concentrate on this. I just simply plug it this in the Bootstrap equation when I have I0 in my thing. So use that. You can write a Mellin transform of this. So multiply with any number, the number of cross ratio, all the cross ratios that you have, and now I can actually do the integral from 0 to infinity. Nobody can stop me from doing an integral of this guy from 0 to infinity. I don't care about the convergence domain anymore. So once I do that, I have some formula. Now, interestingly, as Sandeep already saw through, if you do this integral over xi's, all you will be left with is something like this part, right? This part goes away. And indeed, you have a product of gamma matrices, gamma functions, which includes this new null vectors and the my betas, nothing else. A finite, I have scalars, so only finite number of them. If you had spin, you'll have a sum over spin, but the whole problem of infinite series is gone. That is gone. So I can, so this is, I have a fine bunch of, so for example, for 4 points, I'll have 6 such factors, nothing more. And now I do this. So I have to, I want to plug this in this Bootstrap equation. So I know the mu's that I wrote down by messaging the correlation functions. From there, I can solve for betas which satisfy this equation. So from mu's, I can get the betas in terms of the deltas of the weights of the original fields. Plug them in, and now I have to choose OP consistency. For this guy, OP consistency tells me that beta 1, 2 is 0 in the S channel, and that T channel, these are the two which come together. So beta 1, 4 is 0.
So what was beta?
Betas are the xij to the power betas in the answers. This one.
Oh.
So if once I take that out, because you see, G had these guys. So the betas was sitting in G, I had to choose it. So that OP consistency, choose this betas. Sorry for going over time, but almost there. Right. So once I do that, plug these values in on the both sides. And I have this equation for the Bootstrap, where I have I0 in this channel with a, so I first write down the S channel. Sorry?
I thought the Mellin transformed.
I have not done that yet. So far I just massaged this. I'm saying that the Bootstrap equation can be written as an equation of cross ratios alone. In this particular form, on the left side, I have the cross ratios xi1, xi2, and on the right side, I do a 2 to 4 exchange here. And accordingly, I change the cross ratios. I have an equation of this form. Now, I do a Mellin transform on the left in the sense I do the multiply by xi1 to the power nu1, xi2 to the power nu2 on both sides and integrate. So to change variables accordingly. So when I do that, so if I do that, so because I have to take the integral to xi prime variables on the right side. Once you do that, you actually get this. This becomes this equation. So I have 6 such factors. That's kind of simple. Of course, there are nu1, nu2, all the deltas, and there's D sitting here, nothing else.
Now, this looks very, very tangible and beautiful. I mean, this is the first time people have written it down like that. I mean,
no, if you write up, so Anando, Rajesh, etc., writing down Mellins using the L's, they also had the spins. But yeah, the problem is anyone will trying to do that will have a sum over this L. So the infinite series problem is still there. One has to be cycling.
You don't have it.
I don't have it because I didn't write down the infinite series. I just went over to this.
So which series are you talking about?
In the hypergeometric sum.
I mean, that was the whole point. You got rid of that.
I got rid of that.
So don't you have a very tangible
That's what I'm claiming that it looks better to me.
Yeah. Okay, I'm just making sure I
Yeah,
understand
yeah,
the point.
yeah.
But it does look very.
It looks like, yeah. And I'll always, even for 5 point, I'll only have a bunch of, sorry, where was I? Yeah, here. For 5 points, I'll have any point, I'll have finite number of gammas only.
So somehow this GG, very cleverly chosen. As
Yeah.
you said, GG transform, does some miraculous.
Miracles here, yeah. It looks like the whole problem was the convergence in the infinite series, and this avoids it by using a delta functions. That's the whole idea with they're using delta function anyway. Like in Feynman integrals, we use delta function, etc., to split sums. Basically, it's split singularity.
But it seems, in a sense, it's much better than to drive some Mellin. I don't know the Mellin story.
So when I look at this equation with Mellin space, always the issue comes with this Mach polynomial. Mach polynomials are very difficult. That of course is a
That is-
related
that's
to
right.
a
Infinite
spin,
series.
non-zero spin.
That's it.
Non-zero spin. So no, that spin is not there.
That is not there. So I have to.
If you introduce spin,
This
you
I-
still
I-
get some simple.
I think so, but until I have done it, I cannot really, guarantee. But looks like I have only got rid of one problem. There are some infinite series problem.
Mm.
So the spin problem, I'm not so sure yet. That might still be there.
And if you check that infinite sum expression and this,
That's the next. Yeah, that's it. Yeah.
Right, so just to make sure, the news are functions of.
News are the Mellin parameter.
Oh, so
News are the Mellin.
There is a Mellin transform.
I'm just doing a Mellin transformation from the left.
Oh, okay, I missed something. I thought.
No,
GG,
so-
but it's GG followed by.
GG followed by Mellin. Yeah. Of course, I had to do see, the Xi dependence was there. I had to get rid of the Xi dependence. So you choose Mellin, you can choose any weight function that you like.
Okay.
Yeah, but as long as there's some parameter there, I guess you are fine.
Okay, and just show that last example. And so now this is the bootstrap, and there is.
This has to be true for
every
all
value of new
new.
for every new, right?
Yeah.
On both sides.
Yes.
Okay.
But still there's some simplification. So now let me just
so usually is it true that when people write this, they write it as sum over m, and that should be thought of as a sum over descendants, right? And then here you have resummed that.
listen. So now just for demonstration.
This expression for G scalar block doesn't appear. Oh, see that this description, this
I have only scalars.
yeah, for scalar block, does this appear before or this is the first time?
I have not seen it in this particularly simple form. I'm sure it appears somewhere, but I have not, in some form.
No, I mean as opposed to the infinite sum.
Yeah, so but the infinite sum might sum up to this. That nobody is checking. Yeah, so now I choose a special case where it's the simplest one. All the external deltas are same, delta 0. And then of course, this equation becomes very simple. There will be two factors which are on the same on the both sides, they go away. And so I write it as C square and some L minus R as a sum over delta. Now, C square is a positive number, C being real. So clearly, this can be 0 only when there's a change of sign here. Otherwise, it cannot be 0. That's in some sense is the bound that I was talking about. That it has to be, that's the minimal that has to happen. And so I can locate that by taking a ratio of L by R and C when it goes crosses unity. And so if I did that, this is what I get. I have arbitrarily chosen news to be equal and 3. That's no meaning. D equal to 4 here. I have chosen both deltas, delta 0 and the deltas satisfy the unitarity bound. So I'm plotting this L by R ratio for different deltas here, so there's different delta zeros versus X. So X equal to 0 is the unitarity. So it's clearly, there's all of them actually at some point crosses 1. So I in some sense, I can have a bound. Here I have different dimensions plotted in a similar way for a particular delta 0, which I have again chosen arbitrarily. Now, as Sandeep said, so there's an infinitude of equations like news, but it looks like the bound may depend on mu, but one might actually have a best bound for some mu, like a variation of mu and try to see that. From numerical plots, that's what it looked like to me. I have not done an analysis because varying mu will essentially bring in polylogarithmic functions from the derivative of gammas and all. So analytically, it might be difficult to see. But numerically, it seems that, so if I vary mu, the point it cuts at 1 is slightly changes. But I'm not an expert in numerics, so I have not done a very good job there. But only point I wanted to make is that using this particular fashion is a very simply, I see that there's some kind of bound that I can actually derive, at least. So so that brings.
This is a bound of X versus delta, right? In a sense.
No, this is the ratio. Delta is changing colors.
Okay, so you're saying you change delta
I change
and find an X such that, just so I digest it, you'll find an X such that
the ratio
all delta above it,
that's it.
you will have a change.
No, I mean it at least crosses of the unity. So it means that at some point there's a change in sign, so there's a chance of it's becoming 0.
Right.
If it's on the one side of one always, that there was no chance.
Then you have no chance.
But that's what gives you the bound, right?
That's what gives me the bound. That's a standard way of getting the
Yeah,
bound.
but is it happen that for some values of parameters, right, nus and deltas, that this never crosses one?
So far, I have not seen. I mean, I changed played little bit with this. I have not seen any.
Because that's where
For
we can
example,
rule out that-
For example, if you
rule out
look at
that-
this rate curve for
Yeah,
d equal to 3 here, you see that it misses it here, but it goes and touches it there. So
Exactly.
I want us to do a better scan and all, but I have never, so far, I have not seen any example where it misses the one.
Right.
But yeah, so
Because the way I think of the bound is the impossibility,
impossible.
right? That you have some parameters and for no value of mu, does it go over one, and then that's why it just cannot get.
Okay, now I understand. So suppose there is a value of delta, so that you change x completely, but it never goes past one.
That's
Then
it.
you-
My guess is that that will come only when you put in spin. That's what my guess is. Because then that's another level of difficulty. This is a too simplistic a model actually.
No, but actually, why should you take d equal to one? D equal to one, there is no spin. So maybe there one can.
That's a possibility, yeah.
Then this becomes what you should do in d equal to one.
That is correct.
The nice advantage that.
In d equal to 1, I have some other philosophical problems, so I didn't want to do it. Yeah, I discussed this with Operatim a little bit. In d equal to 1, I have this problem of
Quantum mechanics.
not only conformal quantum mechanics, it's not clear to me what is the meaning of P channel, S channel. I mean, here I have ordered. Changing 2 to 4, etc. seems artificial to me.
People have looked
People have looked, I know. I mean, so,
there is interesting results also.
I know, I mean, what I'm saying is I'm still not fully convinced that this is the
You
right
don't
thing to
have to
do.
change the order. I mean, it can just be this, and then it could either, so let's say disk, and then, or a circle.
No, circle.
Yeah, circle, and then you have T2 points here, and then don't change the order, just take them here.
Like that.
Something like that, yeah. I'm still yet to see the.
Not the
yeah,
U channel.
right.
U channel doesn't.
But then there's a problem of in the circle whether the conformal group might have the Z2 or not, and making it into an RP1 kind of thing. So this is I'm so not fully comfortable. I know that there are results and one can check. I'm not fully comfortable, but yeah, one should do that. I agree. And now that brings, I think, to the end of this lecture. So here are the conclusions, and more or less what I discussed. And sorry for going way over time, I guess.
Not by our standards. You stop before the
Yeah, so we basically talked a little bit about this conformal correlation function representation, and then I wrote the representation of this thing as Mobius transformation before algebras, and took the Fulton-McPherson configuration space and related this representation to a toric GKZ system. And this is first series solution, and then the invariant part of identified GG system, and that helps me in writing the bootstrap equation for a very oversimplified model. So yeah, thank you.
Any more questions?
It's just one
Yeah.
thought thing. All of this was for real delta, or you would have complex.
No, I have not done any. I have not chosen delta to be real so far. I mean, in a numerical plot it is, but otherwise, yeah, because it's not real actually. The point is, if you look at the principal series representation of these groups, these are non-compact groups, you'll always get complex numbers. So typically, it's half plus something.
Right.
In the de Sitter groups, these are basically de Sitter groups or anti-de Sitter group, depending on the set.
Yeah. Just a historical perspective. When was this GG system developed?
GG system, I think, is this century, something very recent, like maybe last 10 years.
What is the
You
GG
mean-
system?
GG
You
system
mean the 20th century or
is
21st?
this 25.
Last
Last 10 years, last 10 years or so. And
Gelfand certainly goes back.
so what they do
Grassmann
essentially is, this I knew that I was right now, this satisfies a GKZ. So with the equation that I wrote down, then they do exactly the same thing. So they write this as some, they will not write Xij, of course, their variables will be different. With some kind of parameters taken out, and then an invariant part. And then they try to find an equation for the invariant part. And it turns out that it also satisfies, there's this combinatorics of betas and null vectors that I wrote down on. So they take that as an integer like
This Schwinger parametric time representation that you wrote down, that
That's a solution of a GG system. So it has a bunch of equations and all, including a difference equation, which might be very interesting actually.
I have a very general
Yes.
question.
So from IMU, you went to finding the IMU as some group transformation and then find difference. So how did you come with that idea?
IMU to differentiate, this is a very standard idea actually. So this is starting from higher secondary, the other 12th level, we know that doing integrals are difficult. Solving differential equations are easier. So whenever you have a complicated integration, it's better to convert it if you have parameters and all. This is actually very standard thing, and we ourselves learned it from these people like Sandeep and all when we talked about Calabi-House and the periods. And,
the hypergeometric, which one? Yeah.
those are exactly so kind of the same type of integrals actually. By the way, there's something something very recent. Feynman integrals are of this kind. And there's a very new, very interesting, nice way of mapping Feynman integrals to the GZ systems by Lee and Pomeranski. And apparently, and Ravindan tells me that there's a drastic change in this whole literature. Like 50,000 graphs, evaluation is now brought down to like 50 or 100 graphs.
Using this GGs.
GKZ. Because these are series solutions, and on a computer, you can evaluate them to arbitrary precisions.
Let me ask, thank you, very beautiful talk, but let me just ask you and everyone a general question, not working in Bootstrap. I mean, it's true that for the icing model, there was a lot of excitement because if I'm right, this operator delta was just at the threshold or something, like something like this happened, right? You got some corners or something. Was it roughly that if delta was, a little below or something, then, for no x it would turn around.
That's right, something like that.
It began to, and at the threshold was because of the icing model, so people were excited. But in general, I'm just wanting to ask, I mean, is this a practical program to actually classify conformal figures? I mean, you get some region for different news for the 4-point, you have to do it for the 5-point, you have to do, I mean, is it actually it's a nice thought, but is it a practical program? You
got the icing model. So similarly, you can imagine
that. Did the icing model brute force, or was it that you got lucky that you
No, there was no luck.
No, there's no luck. No, I think the point is, even in icing model, you committed to a model. You don't.
That went in somewhere.
This is very minor. I mean, you have to say that there are relevant, you specify low-lying operators.
Right.
You say that there is a symmetry first of all, and then say that one relevant operator will set to equal to
and that was enough. But now, okay, but let's say we take 3D. Sorry, I don't want to be, I'm just trying to understand.
No, but I was first this view that there was no luck.
There's no luck.
So the point is that no matter where the CFT is, as you are pushing the bounds down, right, you get these plots, and then if the actual theory is there, then you wouldn't be able to push it further. So that's where the first cusp was observed, right? People don't yet understand, I think, completely why this cusp was there. I mean, what is the explanation of it? And then there was a lower bound also that people got, where people carved the space below also. And got just the point. And for that, the other equation was necessary. It was not like 4-point, 5-point, 6-point, just 2 4-point equations. That's it. I mean, from this point of view, I don't know whether this will be useful in constraining. I mean, maybe it is. I mean, I don't maybe 3 dimensions, you can find some other CFTs this way. But another point of view is to, learn about quantum mechanics. That, trying to get constraints on low energy description of a gravitational theory that is consistent with UV.
I see. So you mean,
that hasn't been successful at all.
But just to understand, let's take a sparse spectrum. Is that what you have?
Yeah.
And now put in the constraints from Bootstrap.
Yeah.
What can it tell you about at least the sparse part?
Yeah, let's say you have given the scale is ADS scale, there is a Planck scale, and now there is a scalar particle coupled to gravity. Let's say, and the low energy person sees the mass particle and the graviton interacting. Right? What can you say about the mass of that? Right? Ideally, given that this is embedded in some large, CFT, should tell you some constraint on that mass. Right?
Interesting.
But I don't think people have done it. So that would be very nice.
That's a fantasy that would be nice.
Yes.
It's a fantastic exercise. Serialized.
Okay, last question, which is, when you go to the cosmology setting, what people call cosmological correlators, right?
Those are in momentum space.
So now I'm coming exactly my question. Now there, for various reasons, especially in inflation, for reasons of connecting to experiment, you want to be in momentum space. And if you try to go from position to momentum space, you have singularities. Not of the kind you had, but just because when you do Fourier transform of these functions, you end up getting singularities. And so I could never, I somehow have this bifurcation in my life that I worked on the conformal correlators in momentum space. And normally you learn CFT in position. I would love to connect the two, but I couldn't do it. And what I'm asking is, have you perhaps looked into it?
I discussed
with all this fancy way of writing things, you can find a.
I discussed a little bit with Sachin at some point. It looked like there are similarities, but on the other hand, okay, let me ask this. So in the momentum space correlators, you assume because in the literature there are different kind of things. One is assume conformality on the space-time part and then do a Fourier. There's another set of work that tells you that you assume conformality on the momentum side itself.
Yeah, exactly. So the work I did was you recast the word identities in momentum space.
So that is
you find solutions.
But that means your conformal part is in the space-time. So you demand conformality in the space-time and do a Fourier. Is that right?
If you like, yes.
And then,
but what was the first alternative?
The other one was that you go to the momentum space first and use the moment in the momentum space. You can ask for a conformality, scaling, etc. in the momentum itself.
But is it different? The what
it's
different.
I've not checked everything, but yeah, there are some differences. There's some old literature about it.
So, this seems totally different, right?
Because there'll be an uncertainty which will tell you.
Seem physically motivated also.
I don't know why they did it.
Space there is a scaling.
Right.
It's a different symmetry group.
Yeah.
Oh, okay. No.
I'm saying it's conformal. It's a conformal group, but in the momentum space itself.
Why 2-point function of two operators?
Okay.
These are some she saw some papers in 70s, etc.
Okay, well, let's leave that aside.
So yeah. So in the usual case. So that will be like doing a Fourier transform of I0, whatever I'm talking about. Essentially that.
But it's an ill-defined Fourier transform.
It's
for reasons I can try to reconstruct. But because you have these power law things in the denominator and you're integrating over x, I don't fully understand why your dimensions worked out the way they did to not get singularities. But anyway, in that Fourier transform problem, you definitely have singularities. And you do get some version of the Abel functions, etc. in sort of momentum space.
But in the 3-point itself, you get the Abel.
Yes.
Right?
Yes, exactly. So, okay, anyway, it seems like a gap in the whole literature. You have the momentum space, conformal, word identities and correlator problem.
I have not written it. So one option is to write. Basically start from whatever I'm doing and writing the Fourier variables. I try to write a differential equation, the Fourier variables part, which should somehow be related to the word identities themselves and compare. I started talking about it, we will go good.
If you want, we can have
we can,
Sachin. Okay.
Sorry, the differential equations in position space will just become algebraic in momentum space, right? Is that not so?
No, the special conformal transformations.
Special conformal transformations.
Yes, so, I wish.
Basically, you have to write down the Fourier transform of, say, the I mu that I'm writing down first, and then look for a differential equation in a similar way. Whatever comes up.
Even scale.
Or Mellin first. So the Mellin and Fourier are kind of similar. You know that, right? So one can actually try to go from Fourier to Mellin in the cosmological setup and try to do it. Yeah, right? That might be slightly easier to tackle. Fortunately, they have not looked into the Mellin part. So what I was suggesting is that it's probably better to go to the Mellin, because for the reasons you are saying, my guess is Mellin will be better, tractable than Fourier.
Okay, for the questions, let's thank Koushik again.